Thank you very much for the opportunity of speaking here and for attending this talk. With the NEST collaboration and their collaborations, we intend to probe a period of the universe between redshifts 30 and 6, approximately. A little bit earlier than that, or closer to us than that, that is still to be converged on, but it's a period that started with cosmic dawn, when the first stars and galaxies appeared, all the way until the epoch of reionization, when those stars and galaxies reionized the intergalactic medium, composed primarily by neutral atomic hydrogen. And those redshifts correspond roughly to 100 million years after the Big Bang, between that time and close to 1 billion years after the Big Bang. Okay? And that is a period that is unexplored. We have almost no constraints on what processes occurred at that time, how fast they occurred, what sources dominated the physics, how the first galaxies and black holes formed, etc. So this is a very ambitious goal for cosmologists today. And again, what we intend to observe is the signal from neutral atomic hydrogen, specifically the 21 centimeter signal. And this signal is produced when the hydrogen atom is in the ground state, but going from the upper ground state to the lower ground state. And that means that the spins of the electron and proton go from parallel to anti-parallel. And when that transition happens, a photon is emitted with a frequency of 1.4 gigahertz, or 21 centimeters. That is the rest frame frequency, but due to cosmological expansion, we expect to detect that signal at lower frequencies. So for instance, for a redshift 6, the frequency goes down to 200 megahertz. And for a redshift of 35, using them as reference here, this frequency goes down to 40 megahertz. So as you can see, now to prove that signal, we need to observe in the VHF range of radio waves. Now, one goal is to measure the sky average intensity or brightness temperature of this 21 centimeter signal. Here in this picture, I show theoretical models for that sky average or global signal and how it evolves from high redshifts to low redshifts, or equivalently from low frequencies to high frequencies, which is the x-axis at the bottom. There is an absorption trough, which I will discuss now here. So the trough is started when the first stars ignite, okay? And so by measuring this signal, we will know when they ignite and what were the fundamental characteristics of these stars. Then the second half of the trough is when the signal goes up, due to heating by the first black holes, heating of the intergalactic medium. So this will give us information about the properties of those black holes, when they turn on, etc. And finally, the signal is extinguished and reaches a brightness temperature of 0 relative to the CMB temperature, okay? And that represents the epoch of reionization. By characterizing how that signal is extinguished and how fast, etc., we will know critical information about the process of reionization on large scales. And that is the equation for most of these physical models. And well, we said that these measurements have to be done at low frequencies. And the ideal place to conduct these cosmological 21 centimeter measurements is the lunar far side, for at least two very important reasons, either with an orbiting instrument or observing from the surface itself. First, the moon shields the instrument from terrestrial radio frequency interference, which, as we know, in the VHF frequency range, that is a very significant artificial contaminant. And also, the moon can shield us from the sun. We want to protect ourselves from activity of the sun and the impact that it could have in different ways. And the second important way in which the far side of the moon is the best place to conduct this measurement is because we can observe without the interference of the Earth's ionosphere. The ionosphere impacts low-frequency radio measurements through its own emission, absorption, and refraction of signals coming from space. And obviously, the lunar environment completely eliminates these effects and complexities introduced into the measurement. But along with the cosmological 21-centimeter signal, with this instrument, we would be observing also diffuse foregrounds. And not only the foregrounds themselves, but the foregrounds as observed by our antenna beam. Okay? And unfortunately, these foregrounds are very large, but they are spectrally smooth. As far as we know, most of the foregrounds are spectrally smooth, and especially the dominant foreground, which corresponds to galactic synchrotron radiation. Okay? Here we can see with the black line a representation of the foreground spectrum, even for this is a low foreground region. And in red, I show the 21-centimeter model, and you can see that it's roughly between 4 and 5 orders of magnitude stronger. So it is very strong, but fortunately, it is spectrally smooth. As part of our collaboration, we are developing a data analysis pipeline at the University of Colorado Boulder that is based on the singular value decomposition technique. So we model this measurement that I presented before as the sum of orthogonal functions. With the SVD method, we produce orthogonal basis functions for the 21-centimeter models and basis functions for the foregrounds and other instrumental aspects. And then using sophisticated Markov chain Monte Carlo parameter estimation algorithms, we estimate the coefficients of those functions, and we can reconstruct the 21-centimeter signal. Here I show a simulation, and so we estimate and reconstruct the signal for different scenarios of measurement noise and instrumental uncertainties. Okay? And more importantly, from that, we can go to estimated physical parameters. Depending on what models we choose for the 21-centimeter signal, we can estimate different types of astrophysical and cosmological parameters of interest. Here, I'm showing as an example the ratio of X-ray and Lyman alpha efficiencies for different star populations in the early universe. This is just an example. So, as I said before, the foregrounds are a very important part of this measurement, the dominant contribution to the temperature. And as I said before, the foregrounds, they vary spatially, but they are spectrally smooth. The 21-centimeter signal is the opposite. It is spatially uniform, but spectrally complex. So we want to separate the two. And one way, well, we would like to constrain these foreground components. And one technique that we are exploring with a ground-based prototype is through modulation of the foregrounds. Okay? So we point at a location on the sky with an instrument, and we either rotate the instrument or we let the sky drift and rotate around that point. And this instrument is a polarization instrument. And what happens is that the Stokes Q parameter, polarization parameter, will contain the frequency-dependent modulation amplitude of the foregrounds alone, while the Stokes eye polarization parameter contains both the foreground and the 21 centimeter signal. So by removing one from the other, we can recover the spectral features of the 21 centimeter signal. This work, at least the conceptual idea has been published, and people from the University of Colorado Boulder and NRAO are working on this ground-based prototype called Cosmic Twilight Polarimeter, or CTP. Okay, and now I will tell you about another ground-based prototype for this measurement. It's called EDGES, Experiment to Detect the Global EOR Signature. This experiment is led by Professor Judd Bowman from Arizona State University. And in fact, it corresponds to two instruments measuring between the first 50 and 100 megahertz, which we call EDGES low band, and the second one between 100 and 200 megahertz, which we call EDGES high band. They target the absorption trough, nominally speaking, and the epoch of reionization transition, respectively. And they are located in the desert of Western Australia at the Murchison Radio Astronomy Observatory. And here I show pictures of the two antennas. This is the low band antenna, this is the high band antenna. For reference, the length is 2 meters and 1 meter, respectively, the length of the antenna panels. And they both have large metal ground planes to reduce the spectral properties of the beam. And here I show a sample of EDGES high band observations. Each of them corresponds to residuals after removing a 5-term polynomial over the range, in this particular case, between 90 and 190 megahertz with the high band system. And I show 40 days. In each case, we are averaging 6 hours of low foregrounds, so low foreground regions. And so after removing those 5 terms, our typical daily RMS residuals are of order 60 millikelvin. So I'm showing this as an example. We have approximately 2 years of data with the high band system and low band system, and we are working on averaging this data and trying to constrain some physical models in preparation for instruments located on the lunar far side. But the important point here is that EDGES implements an extremely accurate absolute calibration, in particular of its front-end receiver, and which also takes into account signal reflections between the receiver and the antenna. The impedance match between the two is not perfect, so with EDGES we have done a lot of work to remove the effect of those reflections. And the other point is that the lunar mission concepts that we are considering will be based on many of these proven techniques. So in summary, the global redshifted 21 centimeter signal is a powerful tool to explore the first luminous objects and the intergalactic medium in the early universe. The lunar far side is an ideal place to conduct this measurement with an orbiting instrument such as DARE, as well as from the surface itself. This is a pristine environment free from RFI and ionospheric effects. We are testing innovative calibration techniques with the CTP and EDGES, and we are developing sophisticated data analysis techniques and testing them through simulations and soon using real ground-based observations. And finally, we acknowledge support from NASA Ames. Thank you very much.
Thank you. Time for one question. Yes, Jim. Rich? That's right. Sorry.
Two questions.
Can you wait for the microphone, please?
In your plot of the spectral feature, you showed a solid line and a dashed line. What was the difference between them?
Here?
No, back.
Near the front, first plot.
Yeah.
Okay.
What's dashed and solid?
Oh, they represent, these are different models for
Just
the
different models.
global 21 centimeter
Okay.
signal, assuming different properties for the first stars and different star types. So
Okay.
some of these models do not account for POP3 stars, some do,
okay.
things like that.
One other question. In your Markov chain reconstruction, the statistical error is small. What's dominating the systematic error that drives the size of that band?
Yeah, well, it's a combination of receiver uncertainty and beam uncertainty.
Okay.
Yes. So our statistical uncertainties can be very low. Can be, for instance, with edges, we have, in practice, very low noise, below 20 millikelvin for different averages of our data. So with a space instrument, we can easily achieve the same.
Okay.
But the uncertainties, at least realistically speaking for now, are dominated by instrumental aspects.
I see. Thanks.
Right, thank you very much.
Thank you.
And so now